that okay? Great. Excellent. Well, I want to start by thanking the organizers for the opportunity to be here today. It's such a great pleasure to be here and enjoying this very nice workshop. So what I want to do today is tell you a story about long-lived multi-level atoms. And hopefully I can convince you these are very interesting systems that are offering great opportunities for quantum simulation and sensing. What I want to focus today is how we can do dissipation engineering, and we can generate states that are dark but also are useful for metrology. So with that, let me start by stating what we mean by long-lived multi-level atoms. And our vision is a little bit narrow here in this talk. It can be generalized to other type of systems, but this case is just biased because experiments, local experiments at Yale. So what we are going to define as long-lived multi-level atoms are atoms that have two outer electrons and therefore are in the second column of the periodic table, or others with similar structure like ytterbium. Why? Because these two outer electrons give the atoms a unique atomic structure with a very long-lived electronic transitions, in particular, for example, for the case of strontium 87, we have a ground state and an excited state that have both a dipole and a spin-forbidden transition. And with that, this state has a lifetime that can be longer than 100 seconds. And that's why this state this optical transition has been the basic of state-of-the-art atomic clocks. And well, we can also have a not as narrow line, but another line, the triple state that have 7.5 kilohertz, that still is much narrower than typical dipole-Arrow transitions. So why we're interested in long-lived? Because we want to explore collective phenomena. And therefore, these rates that we have here, we are going to scale it with the number of atoms. And if we have 10 to the 5, 10 to the 6 atoms, then these rates give us amenable time scales for probing experiments of the order of 100 milliseconds. Or even in this case, we can do 1,000 atoms and it still is realistic. This is one reason. The other reason is that you can see this is J equal to 0. And for the case of fermionic isotopes, then there is a finite nuclear spin, and therefore this opens the possibility to have a very pristine single-level manifold in the ground state. So it has they perfine, but only one. And this has, for example, in the case of strontium, it has a manifold that has 10 different internal states because I is equal to 9.5. But we also have other possibilities in ytterbium that we have only 2 ground state levels or 6 ground state levels. And you will see in this talk that this can be also convenient. So, but the story today is that we can use these multi-level atoms as a playground for exploration of many-body physics. So the punching line of this talk are two specific points. One is that we can use multi-level atoms for generating dark states that are immune to cavity dissipation. That's one, and well, more details can be seen in this paper. And the second story is that we can not only create this dark state, but moreover we can shape these dark states and make them highly squeezed, and therefore useful for metrology. So this is the 2 points that I want to discuss. With that, first let me start by acknowledging my collaborators, the grad students and postdocs that did all the work that I'm going to report. In particular, Asier Pinheiro and Bhuvanesh Sundar have been key in this topic. And of course, collaborations with cavity QED experiments at GILA. James Thompson, we have fantastic discussion, and he's implementing these ideas in his lab. And June now have a new strontium clock that operates with a cavity. All right, so now go to the physics. We have atoms in an optical cavity. Let me start by considering 2 levels for simplicity, but I mean emphasizing that the utility of having long-lived atoms is that we can directly couple these 2 states with the cavity and use these 2 states as a qubits or qudits for our different applications. Moreover, because we have a very narrow transition, then it's unavoidable to have some leakage of light out of the cavity that typically is of the order of 100 kilohertz, and therefore in these systems we are going to be in the bad cavity limit with kappa is much more larger than gamma. For the case of two levels, for simplicity, let's start with that we have a single polarization coupling these two states. Then we can write the Hamiltonian that describes one cavity mode coupled to this two-level system, and we can characterize it via the tuning of the cavity respect to the atomic transition, delta C, and just the atom-light interactions that, as we heard many times yesterday, because the cavity couples to all atoms at the same time. I mean, you can have infinite range interactions, so we don't need to define individual spins, but we go directly and define these collective spin operators that are the sum of each of the individual spin 1/2 atoms for this case. So the atom-light interaction is just the absorption of a photon from the cavity and the excitation of the atoms, a collective spin from ground to excited. And well, we have also the cavity dissipation that is characterized by these jump operators. So the advantage is that in this bad cavity limit, or if we detune the cavity by significant compared to g square of square root of n, in this case, the photons can be absorbed very quickly by the atoms in the cavity, or escape, and therefore very rapidly, and therefore basically the photons in the cavity follow the dipole or the collective dipole of the atom. So in other words, we can adiabatically eliminate the photons in the cavity because their dynamics is very fast. They follow the atoms. And when we do the adiabatic elimination and we replace the cavity in the Hamiltonian, then the elastic part, the real part of the Hamiltonian, gives rise to a collective exchange interaction, S plus S minus. So we heard about flip-flops yesterday, for example, for the river atoms with 1/r cube interactions. Here is exactly the same, but the only difference is that infinite range. So each atom talks to any other atom in the array. And this chi is non-zero for delta C non-zero. And then we have the dissipative part, where this is collective S minus operator, and gamma, that is proportional set by kappa. It gives me the rate of the dissipation. The ratio between these two quantities is set by kappa divided by delta C. So the Hamiltonian opens interesting opportunities, and for example, even for the case of elastic interactions, when you have chi much larger than gamma, we can have a lot of consequences that is interesting from these collective exchange interactions. So for example, the exchange interactions actually facilitates a spin alignment. The exchange interactions want to make the spins all lock together, and therefore preventing spin flips in the array. And for metrology, this is very useful because it wants to enhance the coherence of the systems. And in fact, we have seen this gap protection in the cavity, and also there has been very nice experiments in Monica, for example, that have seen this gap protection. Also, we can drive the cavity, for example, and look at the competition between the exchange and the drive, exploring what is called the Lifkin-Meshkov-Glick model, where we have a system where we can have a competition between the drive and that wants to have the systems atoms oscillate and the exchange interactions, and look at the different regimes between paramagnetic to ferromagnetic. And just because I want to connect to other talks here in the workshop, yesterday we heard beautiful talks trying to understand the different phases of fermions in cavities. And in this case, we want to engineer a synthetic system. So we are not going to really use the fermionic nature of the atoms, but we want to, for example, use the what is called the Anderson-Sedgwick spin mapping that maps a Cooper pair of an empty site into a spin up and down levels of the atoms in the cavity. And we propose in a prior work that with this mapping, we should be able to see different dynamical phases of the order parameter that have been predicted to exist in BCS superconductors, but not seen all of them. So the phases when the order parameter decay dynamically or remains static or oscillates periodically, similar to the time crystal, Wilson time crystal, but in this context, mean field picture. And in fact, the nice part is that James is seeing these dynamical phases in the experiments, and we will, in another opportunity, or I can talk to you about this direction. So this is just to mention that there are great opportunities. But to this talk, I want to focus in the case where elastic interactions are not relevant, and all the dynamics is only set by the superradiance decay. In this case, we can see that the parameter that describes the rate of the dissipation is this capital gamma, that for people more familiar with cavity parameters that prefer cooperativity, this is just the cooperativity times little gamma. Okay, so we heard beautiful talks yesterday about superradiance, and well, of course, that this is a very well-known phenomenon predicted many years ago by Dicke, where you have the collective spontaneous emission of the atoms by placing them by the common interactions with a cavity mode. And what I want to do here is instead to give you a very, very simple picture of superradiance, mean field picture, but this can be useful when I'm going to discuss the multi-level system. So for us, superradiance is nothing else than a self-induced Rabi oscillation. So it's not elastic, it's dissipative, but anyway, the trajectories of Rabi flopping is going to be very similar to the trajectories or the same trajectories that we have from superradiance. To illustrate that is that if you write the mean field equations for superradiant emission, you see that they look identical to the equations that you have for a spin precessing along a fixed axis. In this case, the axis is a vector that is perpendicular to the dipole moment and is constant during the process. So the dipole moment is Sx, Sy, so it's a vector perpendicular to it, and the perpendicular character is because you have an I, so because it's an imaginary process, that's what is that. So basically what happens is that, for example, if I start all the atoms pointing along the C direction, then of course there is no net dipole and there is no dynamics, but you can have a small quantum fluctuation that introduce a tiny dipole moment, for example, along the Y direction, and therefore a perpendicular component along the X direction. Then this starts the superradiant process. And then you can see that you have a net rotation along the X direction, and then the rate of the rotation is not fixed. The rate changes because the dipole moment starts to increase. The rate is going to be maximum when you reach the equator, and then you continue down until you go to the ground state where there is no more dynamics. So that's a simplified picture of superradiance, but it's very useful and equivalent to the one that we saw yesterday when you look at the decay ladder in the permutational symmetric manifold. When you start all atoms in the excited state, there is a quantum fluctuation, and you start this avalanche process that is larger at the equator and then just goes down to the ground state. So this is nevertheless very useful for the next part of the talk. All right, just one comment is that because if you start in the North Pole, the process is driven by a quantum fluctuation. You can see that there is a delay in the emission of the superradiant pulse that scales with the log n, so there is a delay that increases with the particle number in this times renormalized time scale n gamma t, and of course the light intensity have a maximum that scales with n squared. And in fact, this is what have been seen in James' lab, again using strontium 87, that you can see this very small number for gamma, just less than millihertz, but because it has 10 to the 5, 10 to the 6 atoms, then he can clearly see the superradiant pulses with the characteristic delay and a power that scales proportional to n squared. So this has been seen already for two-level atoms. Let me jump to the most interesting case, that is the opposite phenomena of superradiance, that is subradiance, when instead the light emitter is emitted at a lower rate than independent atoms because of quantum interference. So I'm focusing in the special case where the states are dark and therefore there is no superradiant emission at all. So there is not emission at all, zero decay rate. That happens in two-level atoms, but for that to happen, you have to go away the permutationally symmetric manifold. So if you go to the left of the ladder, so Sn half minus 1 and half minus 2, you can see that these are states that don't have anything on the bottom, so you cannot decay down, and therefore these are the dark states. And as we saw yesterday, there has been nice efforts trying to look at this subradiance or dark state in experiments. There has been great progress with the development of arrays of atoms. The challenge is that you have to, in free space, you have to place the atoms much at distance much smaller than the line wavelength, but still there has been nice progress. The idea that we had is that if we can make our life easy and generate a dark state still in the fully permutational manifold, but taking advantage of the multi-level structure of the atoms. So that's kind of the goal. And if I'm going to summarize the story today, that the message that I want to transmit is that if you have two-level atoms, place them in the cavity, illuminate the atoms through a pulse through the cavity, excite them to the excited state, and wait, you will see the superradiant pulse, and then all the atoms are going to be in the ground state. But if you change the story and do exactly the same protocol, but with multi-level atoms, apply a drive, excite them, and then initially you will see a superradiant pulse, but then you will find that there are many atoms that could be stuck in the excited state without decay. And these states not only are dark, but moreover are entangled. And this happens thanks to the multi-level structure. So what I'm going to give you is a very simple picture of this phenomena, and then we can see how we can make it a little bit more exciting. Okay, so for that, we place our atoms in the cavity. Now, instead of being two-level, you can see that there are many levels. And here, in this case, same number of atoms in the levels in the ground than in the excited state, but it doesn't have to be the case. Now, something that is very important in the multi-level case is to use a quantization axis that simplifies the problem. And for us, many cases in the talk, the quantization axis that is very convenient is along the cavity axis. In this case, the two relevant polarization just reduced to the circularly right and left polarization. These are the two allowed polarization of the cavity mode. And therefore, in this picture, we can, as we did for the two-level atoms, we can write a Liouvillean master equation where we have now, instead of one jump operators, we have two jump operators, the right and the left. And in this case, they correspond to the sum of all possible decay channels, for example, for the right polarization, that couple states between M and M plus 1 in this case, or in the case of the left polarization, between M and N minus 1. So you are seeing I'm summing over all possible channel transitions weighted by the Clebsch-Gordon coefficient, each of the corresponding Clebsch-Gordon coefficient. And you can see, sorry for the notation, but this means a collective operator that is the sum over all possible atoms. So they are collective permutational symmetric, we are in the permutational symmetric regime. We are going to be in that regime. Okay, so now let me try to explain superradiance in this multi-level system. And for that, I'm going to start with the simple case that we found. That is what you will find in Ytterbium 171, where you have two ground states, and imagine that you have 4 excited states. In this case, imagine that I'm going to drive my system with right polarization. So in this case, you can see that because these states are never populated, the left polarization will never matter, and we can still have consider a single polarization in a multi-level system. So now the story is that because this basis, we can see that the dipole moment only couples pairs of states. So there, and therefore, this multi-level system can be envisioned as a set of two-level Bloch spheres. So in this case, there are 2. I can have more, 4 or 5. But the advantage is that you can see that because of the way that the system is driven, then there is no coupling between these two through to the drive, and therefore always we are going to have the fixed number of atoms in each of these block spheres. So, and therefore I can define, as we did in the two-level system, collective spin operators with a length. Now is that just determined by the initial preparation. N atoms, N alpha atoms, for example, in the corresponding manifolds, and I have the collective raising and lowering operators and SC. Okay, so now we drive the system, and the drive, imagine that is along the x-axis, for example, and this is different block spheres. And then when I drive the system, then the behavior is the typical precession when you have each of the alpha, the spins in each of the block spheres is going to rotate along an axis that is set by the drive, in this case the x direction, and therefore there is going to be a precession in the z-y plane. And the only difference between the different manifolds is that you are multiplied by the scale by the Klebs-Gordon coefficient. So you have this simple trajectory in the y-z plane. Now, the point is that because we understood the two-level system, in the multi-level system is exactly the same story, that the superradiance decay process in each of the block spheres follow the trajectory of just the drive, because what we see is that the only difference is that the rotation axis is the collective vector perpendicular to the sum of the single dipole operators in each of the spheres. So it's the sum over all of them is a vector perpendicular to this collective dipole moment, but the direction is always fixed and parallel to the drive. So we are going to have the same trajectories, I mean, these are going to decay of each of the block sphere in the YZ plane, as in this case, but just with a different rate. And the advantage is that because the dynamics is in each of the block sphere is exactly the same up to this Klebs-Gordon coefficient, the angle of the rotation is just scaled by C alpha, and we can have a unique equation for the angle theta that is the common for each of the block spheres. So that means that the complicated process of superradiance reduces to a simple equation of a classical particle moving in an extremely viscous medium. So if theta decays or moves in a potential that is, we call the superradiant potential, that we can compute by looking just at the excitation of the atoms, the number of excited states versus the rotation angle. It can be computed just very simple from a Rabi profile. But the interesting part then is that this determines how the superradiant process is going to happen. So in this case of this superradiant potential for this characteristic structure, we see that if the slope of the potential is negative, then the atoms are going to move to the right, and they are going to go down up to a point when the derivative of this potential vanishes, and they're going to be stuck there. So the difference respect to the two-level atoms is that even though the individual dipole moment of each of the spheres can be non-zero, because the total is the sum of them, they can cancel out, and this corresponds to the dark state. So moreover, if you can go in the other case, if the slope is positive, you roll down until you reaches the steady state, the corresponding steady state. So you see that there are stable steady states that are the minima when the second derivative of the potential is positive, and then in the other case where is negative, you have states that are stable at they are states in the mean field, but unstable to quantum fluctuations. So in order to check that this very simple picture is actually correct, then we do simulations using the truncated Wigner approximation, where we look at the initial position in different initial rotation angles and let the system evolve. We increase the number of particles from 100 to 10 to the 4, and nicely we see that exactly the exact dynamics, well, not the exact dynamics, the dynamics with truncated Wigner follows what we expect from the mean field. That is, all this region goes to the ground state, all this region goes to the steady mean field state, and all these points goes to this other mean field dark state. And the regions are separated by sharp transition at the unstable points as expected from the mean field, and the curves converge to the mean field solution with increasing particle number. So that's nice. But of course, this cannot be the full story because I told you that the dark state has to be entangled, and this is something that you can prove. So let's try to analyze what is the entanglement character of these states. For that, we can take advantage of the permutational symmetry of the system that we are using. The scaling is not that nice as in the two-level case. You start to have, if L is the number of levels in each manifold, in the manifold you scale as n L minus 1, the permutational symmetric Hilbert space, but we can solve it exactly for this particular condition from 1 to 30, and you can see that for n equal to 1, the system decays to the ground state. There is no dark state. So that's good because it tells us there is no dark state for a single atom. So the dark states are many body. And moreover, as I increase the number of atoms, then we are going to start to converge to the mean field solution. That's good. But now, if we place the atom, this mean field state is not entangled, of course. It's a product state. If we let the system evolve at this point, and you look what happens, the system is not stable. It's going to decay because of, and go to the real dark state that is entangled. But the point is that it's very close to the mean field state for large particle numbers. So you can see this is the NE of this final population, the excited state, as a function of time compared to the initial population that is the mean field point. And you see that the difference is scales like 1 over n. So you just need to emit a little bit of photons until go to the final dark state. But that means that even though the states are entangled, that is nice, the entanglement is very small as you increase the particle number. So the question is, this is good, but we want to actually use these states for metrology, ideally. So the question is how we can make these states break the standard quantum limit and generate an entangled state. And we heard very nice talk yesterday that maybe a squeeze states could be very powerful for metrology because have one quadrature smaller than the other. So the question is, can we make the states that we have largely squeezed? This has been, of course, typically entangled states are hard to prepare, unfortunately. And if you ask us what would be our dream, if you have a magic genius that asks you what is the magic dream, well, we want to have a state that goes to this steady state, and in the steady state you have a squeeze state. So a robust state that goes to via dissipation to an squeeze state. And well, the important part is that it's possible, even for two-level atoms. There has been a lot of work in the prior years that have shown that if you combine superradiance, but now stabilize it with a drive, then in fact, a superradiance, the combination of the two can generate a spin squeezing, and that is scalable. So let me try to explain this. That is well known, but let me explain you that with the superradiant potential that is useful. So now, for the superradiant equation, I just have to add the drive because now it's on all the time. And then if I'm going to a steady state, this is when this is 0. So when omega is equal to this n gamma, the derivative of the superradiant potential. And for the two-level system, the superradiant potential is just a sine potential, sine squared. And therefore, if you take this condition, then the steady state is when sine of the rotation angle is equal to omega divided by n gamma. That means that when this parameter is larger than 1, there is no a solution, and only exists for angles smaller than pi half. So when you go, the system is stable below the equator, and at the equator is the critical point. So there is a transition, the well-known decay superradiant transition, that is has a steady state below a critical drive, and at the mean field keeps rotating all the time if you go to a very strong drive. And in terms of the superradiant potential, as expected, when the second derivative is positive, then it's stable. In the second derivative being negative, it's unstable to quantum fluctuations up to the drive. And in this, at the point when the second derivative is equal to 0, you have a critical point. And the interesting part is that at the critical point, the system becomes highly entangled, or it scales like n to the minus 1/3, so it's a squeeze. The only problem is that if you turn off the drive at the critical point, then the entanglement disappears. So we want to have something stable. So the main idea is that the superradiant potential is all what we need to even understand where we can create a squeezing in the multilevel system. Because if you start with a superposition of two particles in this low manifold, that is, beta is the admixing angle of the superposition, you can write a superradiant potential as a function of this beta and the angle theta, the rotation angle, and you can see when you write the superradiant potential that there are points where the second derivative is 0. These are the critical points, and moreover, there are points where there are the dark states where the derivative is 0 at the minimum of the potential, and moreover, there are points where you have the state that is critical and dark. So that's where we want to go. So these are calculations, numerical calculations of the spin squeezing. The interesting part is that when you have multi-level system, with one polarization, you get not only one curvature, squeeze quadrature, but we get two. I can explain more details why, but there are two squeeze quadrature, and you can see that the squeezing is scalable along these critical lines, as expected from the superradiant potential. And moreover, at this saddle point that is critical and dark, that's where the squeezing is generated. And to show you that, so these are simulations where we go to this line, this pink line where you have the dark and critical point here. So we do simulations where you drive the system, place them very close to the saddle point, turn off the drive, and let it decay. And then you wait, and then when you wait, you have two squeeze quadratures with a squeezing that scales with the particle number as n to the minus 1/4. It's not as good as the two-level system, but it still is a squeeze. And there is another protocol where you instead can prepare the system in a critical line, and then you have to put the drive on. And if you look at the dynamics, there are two squeeze quadratures that, you start with an entangled state, then you form the two squeeze quadratures, two anti-squeeze quadratures, and then you generate entanglement. But then if you want to preserve it, you rotate the state. You have to transfer the entanglement. So you rotate the state by a single particle drive onto the dark point. But then if you let it like this, it's going to decay the squeezing. So what you have to do is to add specific rotations. I cannot tell you here what are the specific rotations, but you can have some specific rotations where the two squeeze quadratures are conserved, and you can keep the state in a dark point that it remains entangled. I'm running out of time perhaps, so just very briefly how we computed all of this is very simple. To include the quantum fluctuations, what you only need to do is to develop a bosonic picture of the spin system. So if you have, for example, for the two-level system, you have the spin pointing along the y direction. This is the y plus y minus y. All the atoms are along the y direction. So you can write the erasing operator in this basis in terms of Schwinger bosons, but because one is completely populated, you replace by a C number, then you express the quadratures as perpendiculars to the block vector as a bosonic operators, and then you can have just P and X quadratures where the dynamics can happen, and you can compute in a quadratic picture the variance of these XP quadratures, and then squeezing is just when one of the quadratures is smaller than 1. And that happens, for example, in two-level system during the driving board. So you can do the same protocol, same recipe, but with more Schwinger bosons, more quadratures, but repeat the same procedure, and then that's done. I'm finishing here just saying that I discussed one polarization. Similar physics happen, a little bit more complicated when you have two polarizations, but still the superradiant potential is super useful. So you just write the superradiant potential for each of the two polarizations and look at the positions where the two are stable, and you can have, instead of two squeeze quadratures, 4 squeeze quadratures at the critical points of the two superradiant potentials. So these points here are points where you can have four spin quadratures, and the utility of that is that we can use it for multi-parameter estimation. If you have to estimate very accurately different parameters, you can use all these different quadratures for that. And with that, I'm running out of time, so hopefully I convinced you that multi-level atoms are useful and can be interesting for generating entanglement in a simple way. And well, we want to understand what are the optimal interferometry protocols to use all these quadratures, and maybe see if we can generate even more in other ways. And with that, thank you for your attention.
Thank you so much for this wonderful talk. Questions? We have a couple of minutes here.
When you deviate from the fine-tuning, so to say, how sensitive it is?
Now depends on the superradiant potential. If you have only one quadrature, it's very stable. I mean, to go to the minimum at this point. But if you have an unstable point, it can be bad. So now you have two different polarizations. Then you can be very unstable to one of the points. Is that your question?
Yes. Yes. So, how much do you deviate? How quick do you deviate from the optimal? When you deviate a little bit, so to say.
But depends on the form of the superradiant potential. So it's just the question is theta dot is minus b db d theta. Mm-hmm. So the deviation is set by the rate of the superradiant potential at the point when you start. Mm-hmm. Does that make sense?
So with these dark states, how does the picture change, or does it depend on the cooperativity of the cavity and the ratio between G kappa gamma?
Yes, no, this is an excellent question. So these dark states are only dark states to cavity dissipation, but there are no dark states to emission in all polarizations. So there is a separation, however, of scales, because in the n gamma is the scales. I mean, if you have a NC is very large, then you have a very important separation between the single particle spontaneous emission and the collective emission. So you will be dark for the time scale that is separated from the time when you start to decay because of single particle process. Does that make sense? Mm-hmm. Mm-hmm. So you want a lot of atoms.
Yeah, a lot of atoms.
Mm-hmm.
Actually, my question was very similar. So.
Mm-hmm.
Related to the last questions. So, I mean, you said it's the cavity dissipation is key, or the dark state are dark states with respect to cavity dissipation. And do you have an intuitive picture? I mean, cavity dissipation, the big difference is that it's dissipation along one mode. So how,
yes.
What's your thinking
It's not
about
only
that?
but also there is only two polarizations. In free space, there are three polarizations because you can emit into all different directions. So the cavity direction is possible because you can leak. So no, it can be completely off. I mean, you can decay totally from single particle spontaneous emission. But the ideal scenario is that you have an array of atoms in an ordered array that is dark to single particle emission, and maybe you can also try to see how you combine it. I mean, we have not done that, but the ideal world, you want to combine Fermi blocking, Pauli blocking with so imagine that you prepare two atoms per trap, so and in a singlet state. So this state is dark to single particle dissipation, and you can form a spin that can still talk to the cavity. I mean, we have not done that, but this could be the ideal situation, combine states that are dark to single particle drive and also dark to cavity. They still not work out that.
Thank you.
Great. So perhaps in the interest of time, let's thank Anna Maria again. And